It's just a lot of calculation. Okay. So the next part is he calculates the expectation value of the SY, XZ, and SX. All right. Now, when it comes to that, you guys should make sure you can do each one of those steps. All right. He finds that essentially, so this is where forget my alpha here, or my theta there, but here's the conclusion, is that when he calculates the expectation values, he finds the expectation value of S, that's Z, equals cosine theta. He computes the expectation value of Sx, and that equals sine theta cosine phi, and of Sy equal sine theta sine phi. All right, and where phi in particular is, let me put this in explicitly, phi is gamma b0t. So this is cosine of gamma b0t of gamma b0t. So these are the expectation values. All right? And so what he wants you to do next is recognize that, look, this looks just like spherical coordinates. So if I had spherical coordinates, right, this is my polar angle, and my polar angle is theta. All right? And cosine of this polar angle theta gives you this amount, which is my SZ. And theta is that arbitrary angle that came in over here. Oh, I guess I did use the right angle. Okay? So that's arbitrary angle and equals constant. All right, now, how to interpret these things? Well, if I'm looking at the sine of the theta, what I'm doing, I'm looking at this amount, which if you project it down here to the x, y, z plane, if you projected that down, this amount right here is sine theta, and this is, so project it down, look at the shadow down, project that down here, it's sine theta. All right, then what you see is that this angle right here is the azimuthal angle, phi. All right, and the azimuthal angle, this would be the cosine, which would be the x. And then this would be the sine part, which would be the y. I didn't draw my, my right angles very well. All right, but what you recognize is that this is just something in a, this is just a vector, all right, that always has a constant z projection, but that it's this angle phi right there, which is gamma b0t. So here's a time right here. So what does this represent? So that has to be omega, which equals a radians per second. So that when you multiply it times a second, it becomes radians, which is the argument for the sine or the cosine. And so you recognize omega as an angular velocity. And omega equals 2 pi times f. So f equals omega over 2 pi. That equals the Larmor frequency. And here it's going to equal, it's equal gamma b0 over 2 pi. And if you check that out, if you check out the units of that, that will have a unit of hertz. Okay, so when you do this, when you when you put a spin particle with a magnetic dipole moment in a magnetic field, the picture of how this thing reacts is that it rotates about that magnetic field. All right, that you get a rotation about the magnetic field, and the rotation frequency is proportional to, most importantly, the magnetic field. All right. So, and this is really important because when we do NMR, nuclear magnetic resonance with protons, the proton is a magnetic dipole. If you put the proton in a constant magnetic field, what is that proton going to do? That's going to precess about that magnetic field, right? Is it going to have a certain frequency of precession?
Yes.
It's going to be proportional to
Whatever
V
the
zero.
magnetic field is.
And therefore, I can tune into that precession frequency and, you know, essentially talk to that proton. Yeah, you tune into a proton, like Buckethead does, I'm sure. The guy is amazing.
Tunes into chickens. I don't know what he tunes into, but
You gotta look at, look at videos of Buckethead, it's very strange.
I got a question about
Yeah.
this. Like when you do the Stern Gerlach, you're gonna be doing it with, say, some larger atom.
Yep,
Will there be a Zeeman effect too in the magnetic field?
so,
When you apply a magnetic field, you get a transition.
yeah, so if you're gonna have a magnetic field,
That'll add another trend to the Hamiltonian order.
yeah, yeah.
But
So
maybe
what
it's-
that will
But it's
do-
small maybe.
Well, what that will do is that will change that. So here's the scoop there. If you were to do spectroscopy of the electron energy levels for an atom in a Zeeman thing, then you'd see that it was Zeeman shifted, that there'd be an energy shift. But in the Stern-Gerlach experiment, you're not looking at the shift in energy of the electron. What you're doing is looking at the force on the electron that pushes the atom in a state up or down. Okay? I think that's the final answer.
Mm.
Yeah. But yeah, I never thought of that, but you definitely have a Zeeman shift in the electron energy levels. But you know, the goal out of there is to calculate the force that comes out.
so if we were to do like a finer experiment, we find like hyperfine splitting of those two.
Yeah, exactly. So if you could do some type of spectroscopy on whatever atom is going through, you'd find out. Like if you're going to cool and trap through, you know, through a Stern-Gerlach, you would have to really know the B fields to find out how much the energy level should.
But you couldn't cool the trap because they have motion.
Yeah, the whole result of the Stern-Gerlach is to give it a force out. Yeah, so I mean, it would be contrary, of course. I was just trying to find a place where you want to know the resonance. Okay. All right. So look, that problem is great. The Stern-Gerlach problem is great. There's not much detail there. And so the problem I really want you to be able to do is the Moore precession problem. All right. Griffiths mentions all the difficulty too with you know, doing a real Stern-Gerlach. Okay. All right. Hey, so let me copy this, and then I'm going to do the spin and Clebsch coordinates. Okay. So let me make copies of this.